Hi guys, good morning.
Good morning, sir.
So should we start? So we were seeing hybridization, isn't it? Right. So I think everybody remember what is the shortcut, right? So can you tell me the formula for finding the steric number that will find me the hybridization?
The
What
number
is
of atoms bonded to the central atom plus number of lone pairs in the central atom.
good, right? So that was the formula. So with that, I was easily able to find what will be the hybridization of a central atom in any molecule for that matter. Isn't it? And then we also saw, right? So there are like certain prerequisites we already saw, like saying that pi electrons, that is the electrons involving in pi bond, will be outside the hybridized orbitals, right? And I told you this thing also, the number of pi bonds in a molecule. I asked you to write a note, if you can remember. The number of pi bonds in a molecule is equal to the number of unpaired electrons after the hybridization, right? Number of unpaired electrons after the hybridization. So I think we saw so many examples like that, right? Okay, so we started with steric number 2 with obviously sp hybridization, right? That's what we started with, right? And then we saw, I think, 3 examples: CO2, right, which had 2 pi bonds, and then we went on to see BeCl2, which doesn't have any pi bonds, and then we went on to see alkyne, that is C2H4, right? All these things we saw. And then I introduced you to the concept of VSCPR, right? So VSCPR says that, okay, what is the statement for VSCPR? Can someone tell? What was the statement for VSCPR?
The shape of the molecule should be in such a way that the electrons in the valence shell suffer minimum repulsion.
Exactly. So the whole thing about shape of the molecule, right? So a theory of hybridization talks about how the covalent bond is formed. Say there are some shortcomings in VBT. Now I excite the electron so that I have hybridized orbitals. All these things are explained. But the shape, right? But the shape of the molecule is going to get explained with the help of VSEPR, right? So now I have to make sure that the electrons in the valence shell of the central atom suffers minimum repulsion, right? So now how can I make sure that they suffer minimum repulsion? If I can increase the distance between the, if I can increase the distance between the electrons, right, in the valence shell, obviously I'll be able to reduce the amount of repulsion that is there in the molecule, right? Okay, so if for that case, if I have a molecule, this thing, what is that? Uh, if I have sp hybridized S is equal to 2, that is steric number 2 is the molecule, you can easily see that the maximum distance which I can be play. Okay, now before that, so we are talking about electrons in the valence shell and obviously in the central atom, right? So you can see that the electrons which are there in the valence shell can be in 2 forms in the molecule. One, the electrons can involve in bonding like this. You can see that there are 2 electrons. Second, there are 2 electrons which are like involving in bonding here from the A. Other than that, if I have any lone pair, so those are the 2 types of electrons they can have in the valence shell of the atom, either one involving in bonding or the one which is not involving in bonding, which can be in the form of a lone pair, right? So I have to make sure the repulsions between these 2 types of electron is minimum, right? Now you have to choose a case like, for example, sometimes you have to give more priority to one kind of repulsion, because that repulsion is going to be more dominant, right? So I gave you an order also, if you can remember: lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion, right? Okay, so if particularly in this case, if I have AB2 type of molecule, right? So I don't have lone pair, I don't have lone pair bond pair, because there are no lone pairs present, first of all, right? So I can easily say that only bond pair repulsions exist, right? So I have to make sure that this repulsion, that is the bond pair repulsion, should be minimum. And the easiest way to make sure that it is minimum is by putting the bond pairs of this AB bond and AB bond maximum distance apart. And obviously, if I put that, the shape is going to be what is called as my linear shape, and the bond angle is 180 degree. Now, please understand, whenever I say bond angle, it talks about the angle of bonding atom, central atom, bonding atom. Not only in this case, see, bonding atom, central atom, bonding atom, that bond angle, right? So that bond angle here is going to be 180 degrees. Okay, so these are all the examples. These are the last class. These are the things which we saw, isn't it? So we'll move on. We'll move on to see different hybridization. Now we saw SP, right? Now we'll go to steric number 3, right? We'll go to steric number 3 and see what happens. Guys, any doubts till now? This one all we saw last class only. Like we didn't introduce anything new today yet, right? Okay. Cool. So let me go for steric number 3, right? So if I have steric number 3, I know what will be the hybridization. Hybridization would be sp2 hybridization. Okay, right. Now in sp2, in steric number 3 itself, I can have 2 types of combinations, right? What can be the 2 types of combination? The first combination can be like this, AB3 type of molecule. What do you mean by this? There are 3 bonding atoms. So obviously there are 3 bonding atoms, no lone pair. Number of atoms bonded to the central atom is 3, no lone pair. So steric number is 3, sp2 hybridized, right? Now there can be one more combination possible. Now instead of having 3 bond pairs, right, or instead of having 3 bonding electrons, I can have something like this, AB2L. Now I told you L represents lone pair, right? L represents lone pair. So again you can see the steric number is 3, but instead of having 3 bonding atoms, I have 2 bonding atoms and 1 lone pair, right? 3 bonding atoms and 1 lone pair. Okay. So like why didn't I talk about this when I in the last case when I had steric number 2? That means I talked only about AB2 in case of steric number 2. Why didn't I speak about ABL? ABL also I can write, right? This combination is theoretically possible, isn't it? 1 bond pair and 1 lone pair. That also is steric number 2. But this kind of cases you are not going to see much. Actually, you will not see. Okay, at least for the central atoms, you will never see this kind of combination coming. So this is not possible. Okay, but in steric number 3, AB3 is possible, AB2L is also possible. So we'll take examples for both of them, and I'll try to see what we can do about it. Okay, so first we'll start with AB3. We'll take some examples and we'll see how the hybridization is made and all that. Okay, the best example I can take under this is BF3. Okay, boron trifluoride. You can see boron is central atom. There are 3 fluorine atoms as bonding atoms, no lone pair, right? So obviously this comes under AB3 type of molecule. Okay, so now we already know what is the hybridization. We just have to prove it, right? So boron is having an atomic number of 5, so it will have 1s2, 2s2, 2p1. Obviously this is grounds. Okay, so now if I make the valence shell, if I draw the orbital diagrams, so you'll see that this is my ground state, right? Now I told you that whenever you're going for hybridization, all the electrons which are there in the valence shell should be unpaired first, right? All the paired electrons. So you can see that this is 1 paired electron here. So whenever you see this coming, you have to make sure that that is going to go to the next excited state, that is the next empty orbital. Okay, so if I now go to the excited state, so you will see that in 2s I have 1 electron and in 2p I have 2 electrons. No problem. Okay, now what is the hybridization? Hybridization is sp3, sorry, sp2, correct? So I can see here I have 1 s orbital, 2 p orbitals having single electrons, so they will come together, mix together to form 3 numbers of sp2 hybridized orbitals, each having 1 electron, right? Now what is going to happen? Now these are the hybridized orbitals. Now these hybridized orbitals are going to overlap. These hybridized orbitals are going to overlap with the pure atomic orbitals of fluorine. right? So I have 3 fluorine atoms. If I can get another color, it will be helpful. Do I have? Yes. So there are going to be 3 fluorine atoms, each giving one electron. So done, right? So 3 sigma bonds are done. Okay, fine. We understood that the 3 sigma bonds are formed with overlap of hybrid orbitals and the atomic orbitals. Okay, and so you can see that after the hybridization, there are no pi electrons also, no pi bond, and there are no lone pairs, right? So again, the only kind of repulsion which I have to make sure is minimum is the bond pair repulsion, isn't it? The bond pair repulsion, right? And I have to make sure that the distance between these three bond pairs are there. So I have to make sure that these 3 bond pairs are maximum distance away from each other, right? And the best way to put this is like this: B, F, F, 3. I mean B, F, F, B, F, 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 right? So you can see this particular shape. This particular shape is what is called as. So you can see that a triangle is getting formed here, right? So this particular shape is what is called as trigonal planar. So the terms are very important, right? You don't have to mug up the shapes also. It's very simple. I have a triangle in the same plane, right? Triangle in one plane, trigonal planar, right? Okay. Can you guess what will be the bond angle here?
60 degrees.
60 degrees. See, bond angle.
90 degrees.
Okay. See, how do you talk about bond angle? I already told you bond angle should be low. I mean, bonding electron, central atom, bonding atom, right? So if you cannot take this bond angle, no, this you cannot take this angle. This is not the bond angle. What will be the bond angle? This will be the bond angle. Bonding atom, central atom, bonding atom, bonding atom, central atom, bonding atom. Again, this one can be the bond angle, right? Just because you see it's an equilateral triangle, you cannot say that this angle, this is the bond angle and that is 60 degree. No, it should be bonding atom, central atom, bonding atom. So this angle is what I have to take for. Tell me what will be that angle?
120.
Yes, very simple, right? Totally 360. Around the point, totally 360 divided by 3, right? So obviously here the bond angle is 120 degrees. Here the bond angle is 120 degrees. Okay. So remember for AB3 type of molecule, anyways, you don't have to anyways at the end of all this, we'll make a very big table, right? So we'll allot all these entries there. Okay. For now, we'll see one by one. No problem. Okay. So when I have AB3 type of molecule, obviously the shape is going to be trigonal planar shape, right? And the bond angle is 120 degrees. Okay, right. Fine. So there is nothing such as such happening here. Cool. Now, I want to introduce you to one thing, right? So guys, please take this down. I will introduce you to the concept of geometry and shape. There is a difference between these two. Okay. So there is something called as geometry of a molecule, and there is something called as shape of the molecule. Okay. Now, till now, you didn't see any lone pair as such coming, right? So there is no segregation between shape and geometry, right? So I can tell that shape is equal to geometry, or I'd say shape and geometry are same if no lone pairs, right? Shape and geometry are same if there are no lone pairs on the central atom. That you can make sure. Okay, fine. So how do I go about it is for a particular hybridization, right? For a particular hybridization, any type of hybridization for that matter, right? If you don't have any lone pair, obviously all the hybridized orbitals contains only the bond pairs, right? So VSEPR can easily predict what will be the geometry of the molecule, right? So that is what is meant trigonal planar or linear or in this case, shape and geometry are same. Or instead of explaining like this, let me take an example. I told you the problem comes, the difference between geometry and shape will come into the picture if I have a lone pair. If I have a lone pair. Okay, fine. So let me take an example. We'll take for this sp2 hybridization itself, we'll take an example. Right, we'll see whether I can get something out. Okay. Fine. So let me look into AB2L type of molecules. Again, steric number is 3. 2 bonding atoms and 1 lone pair. Right? Okay. Now, if at all, say, now in this case, all 3 are bond pairs. Right? All 3 are bond pairs. So, like this also is expected to have a shape like this. Right? This particular molecule also is expected to have a shape like this. But its shape is not going to be like this. But the geometry is going to be like this. The geometry is going to be my trigonal planar. No problem. Right? The geometry is going to be my trigonal planar. So how will I draw it? A, B, B, and a lone pair. Right? So, or, okay. This is my geometry. Trigonal planar. Okay, this is my geometry. Okay. But if I talk about the shape, right? Now the difference is you just whatever the hybrid for a particular hybridization, geometry is constant. For sp hybridization, it is linear. For sp2 hybridization, it is trigonal planar. For sp3 hybridization, it is tetragonal. So all again we'll see that. So all these things are constant. All these things are constant. That is for geometry. For a particular hybridization, it is same. Okay. But if I talk about the shape, in shape, what I'm going to do is, so geometry, you will place the lone pair in some pair, right? In geometry, you will place the lone pair in any one of this. Okay. So now what I have to see is the effect of repulsion. The effect of repulsion. So first time you are experiencing what is that? The lone pair bond pair repulsion, right? There's a lone pair, there's a bond pair. So this repulsion you will see, isn't it? This repulsion you will see. Okay. So the consequence of this, and there is going to be something happening to this geometry, and obviously there is where the shape is going to come into the picture. There is where the shape is going to come into the picture, right? Okay, so in this case, the shape I'll be able to easily call it as, now see, because of this lone pair bond pair repulsion, what is going to happen? This bond and this bond are trying to come together, closer together. Why? Now you can ask me, sir, bond pair repulsion is increasing. So if I make them come closer like this, like, okay, how to put it? Say it comes from here, it comes from here. They're going to come like this together because of this repulsion. Then you can ask me, sir, what about bond pair repulsion? Yes, that will be increasing. But which has to be given more priority? More priority has to be given to lone pair bond pair repulsion. Here I have bond pair. Here I have lone pair bond pair repulsion, right? So lone pair bond pair repulsion should be given more priority. So these two bonds will come together, constrict like this. Okay. So the expected shape, the geometry is basically going to be my trigonal planar, but the shape is not going to be trigonal planar. The shape is going to be something like this. So what you do generally in shape is that you don't include the lone pair in the shape, right? You don't include the lone pair in the shape actually, right? So this is the shape of the molecule, and if at all you want, you can put the lone pair here, but the shape is not going to be trigonal planar. The shape is going to be called as bent shape. Why? Because if I just don't consider this lone pair, right? If I don't consider this lone pair, what are you seeing? It's like this, a bent shape. Like both the bonds are coming together like this, right? This is the bent shape. Okay. So don't worry, guys. Like you will see, like you will understand the significance of difference between geometry and lone pair when I go for more and more and more molecules. Okay, please understand that. Okay, for now, if at all I have AB2L, I have lone pair bond pair repulsion. So it cannot be exactly like this, 120 degree, everything 120 degree apart. It's not possible. So due to the lone pair bond pair repulsion, the bond is going to constrict like this, so that I'm going to have a bent shape, and the geometry is trigonal planar. The geometry is trigonal planar. Okay, so we'll take an example for this. We'll see how actually this happens. So AB2L, I have to take an example. I think NO2 will be a good example. It will take the example of NO2. So guys, any doubts you have, right? If at all you have any doubts regarding shape and geometry, hold it. You will eventually get it clear. Okay. Other than that, anything how the base shape is bent, or say some other doubt you have?
I had doubt only in that bent, sir. Like,
Bent.
what happens
Okay.
when it's bent?
Nothing happens. This is the state. This is where this is how the structure is stable. What happens if it's bent? I'm telling that bent shape is happening because of stability.
So that means
Because
the
certain
bonds
stability.
come closer together.
Exactly. So, or how do I put it is, now say I have a linear shape. Okay. Okay, I
Yes,
have a
sir.
linear shape. Now, there are no lone pairs. Now, if I put a lone pair here, can the shape exist like this?
No, sir.
No, because the lone pair bond pair repulsion will increase. These two bonds will try to come away from the lone pair. That these
Yes,
two bonds
sir.
will try to come away from the lone pair and eventually end up in this kind of shape.
Okay, sir. Now I understood.
Understood? Okay, fine. So we'll take some example for, like, say, how do we go about the hybridization, and where do we place the lone pair? All these things we'll see. Okay. Okay, so let me take NO2 minus. Okay, NO2 minus. Okay, first you need to know the structure. I mean, structure in the sense the Lewis dot structure. If you know, it's better, or else you need to draw the Lewis dot structure and then see exactly how is it. Like, I don't have to draw; it's pretty easy for me. So N double bond O, 1 O minus. Done. This is what is the shape. This is what is the structure for NO2 minus. Okay, fine. Now you can easily tell what will be the, now we are still in S is equal to 3, steric number 3, and we are looking at AB2L type of molecule, right? So you can see that there are two bonding atoms, two oxygen atoms, and nitrogen atom has 5 valence electrons, right? So I have 1, 2, 3, 3 involving in bonding, right? So definitely I have one lone pair. 2 electrons are left out, one lone pair. No problem. So 2 bonding atoms and 1 lone pair. Done? Right? Okay. So let me see how is it undergo. So obviously the hybridization here is going to be sp2. That is understood. 2 bonding atoms and 1 lone pair. Steric number is 3. sp2 hybridization. Okay. So now again we'll try to prove how it is sp2 hybridization. Can you try? Or wait, this I'll do. Next thing you try, because I have a lone pair and all. Okay. Fine. So nitrogen is having 1s2, 2s2, 2p3. So in 2s, 2 electrons. In 2p, 2 electrons. Or 3 electrons, actually. Right. Okay. Now, there's a problem, isn't it? What problem? I have a paired electron in S, right? In last cases, what I did, I made this paired electron get unpaired. That is, I made it single, right? And I make sure that the one of the electron is going to go to the empty orbital, which is there in the next, right? But here, what you see is the 2p orbitals are filled. Already I have 1 electron here, correct? Right? But what you have to understand is there are two things which are going to be placed in a hybridized orbital. One is the sigma electrons, right? The electrons which are going to involve in the sigma bond will be placed in the what is that, hybridized orbital. Other than that, there is one more thing which is placed. What is that? I'm telling, in the hybridized orbitals, right? I place sigma electrons. Okay, that is understood. What other things I place in the sigma or in the hybrid orbitals? What are the things I place? We didn't say example, but I told you, right, which and all will be coming in the hybridized orbital and which cannot come inside hybridized orbital. What are they?
Pi, sir, 5 orbitals.
Sorry?
Pi orbitals.
Pi orbitals will come outside the hybridization. Okay, that is correct. Inside the hybridization? Okay, guys, please understand, inside the hybridization, I have to make sure the sigma electrons are there as well as lone pairs, if any, are there in the central atom. They also should come inside the hybridization. Please make sure. Okay, so inside the hybridized orbitals, I need to put the sigma electrons as well as the lone pairs on the central atom, obviously. Right, these two should be inside the hybridization. The pi bond should be, the pi electron should be outside the hybridization. Okay, so now tell me, okay, now this is made sure. So now, now what is the hybridization here? Hybridization is sp2, isn't it? For this, hybridization is sp2. So I'll try to make sp2. Okay, so like if at all you want, you can shift the electron to the last orbital. We'll see how is it going. Okay, so now I say I have sp2 hybridization done. Okay, but what you know is nitrogen has one lone pair. Nitrogen has one lone pair. So what you have to understand is there are going to be 3 sp2 hybridized orbitals, isn't it? 1s and 2p are combining. There are going to be 3 sp2 hybridized orbitals, and you can see that there are only 2 sigma bonds. One sigma bond between this nitrogen and oxygen, and the one sigma bond between nitrogen and this oxygen. Understood? So 2 of them are understood, right? One sp2 and another sp2 are involved in sigma bond formation. Done. What about the third one? Third one is actually going to accommodate the lone pair. The third one is actually going to accommodate the lone pair. So you should not put the electron here. You should put the electron here. You should put the electron here, or you can put here, here, or here, anywhere. But it should be inside the hybridized orbital, right? So now if I draw the hybridized orbital, 2 of them will be having single electron, and the other one is going to have a lone pair. The other one is going to have a lone pair. So obviously now what is going to happen? Oxygen atom is going to come. Oxygen atom is going to come. There are going to be 2 sigma bonds. Done. Okay. And there is one lone pair. Now what else I have to account for in this molecule?
One pi bond.
Exactly. So you can see that there is a double bond here, right? There is one pi bond between this nitrogen and this oxygen, right? So now whatever the trick I told you is helping here, you can see that after the hybridization, whatever is the number of unpaired electron, that would be the number of pi bonds. So you can see after the hybridization is over, there is still one unpaired electron left. Sorry, correct. There is still one unpaired electron left. So this, I would say, this unpaired electron and oxygen will have an unpaired electron in the p orbital. They will laterally overlap to form this bond. Okay, so there are things which you learned now is that the only thing actually you learned now is that the lone pair on the central atom should be placed inside the hybridized orbital. That's it. That's the only thing you learned. Okay, the lone pair, see where is it? The lone pair, oh, okay. So if I just do oxygen, this electrons are coming from oxygen, so the sigma bond is formed, but you can see the third hybridized orbital is having a lone pair. Okay, so obviously here the shape is going to be how? If I just draw the shape, okay, I'll draw it here. So you can see that it is going to have a bent shaped. It is going to have a bent shaped, isn't it? Right? So you can see this is here, this is here, there's a lone pair. If at all this lone pair was not there, it would have been linear. Right? If this lone pair would have been not there, this would have been linear. But because of the presence of this lone pair, the lone pair bond pair repulsion, the bonds are going to constrict, bringing out bent, or it is also called as V-shaped molecule. Bent or V-shaped molecule. Any doubt, guys? Any doubts?
No, sir.
Is everything? We'll see more and more and more example. I can understand it is little clumsy here, but as I see more and more and more example, it is going to come at your fingertips. Do not worry. Okay, fine. The shape is this. What is the geometry?
Trigonal planar.
Exactly. You don't have to worry about what number, whether I have lone pair or bond pair, whatever it is. The moment you see sp2 hybridization, it is going to be trigonal planar. That's it. Okay. So fine. So we saw now sp2 hybridization happening, one without lone pair, one with lone pair, and you saw there's a bond, there's a pi bond also. You saw how to place it. Okay. We'll take more example. Now we'll go to sp3. Okay, we'll take so many examples. Right. Or in sp2 hybridization itself, I can have one more example, and you are going to do it. Okay, so I have C2H C2H4. I have C2H4. This is my ethene, right? Hope you remember. This is my ethene. First, try draw the structure. I want you to find what is the hybridization, and I want you to prove it with the help of this orbital diagram. If at all you have pi bonds, you have to account for it. All these things you have to do. I'll give you 2 minutes. Quickly do it. And in that time, I'll just come back. Close this. So first step is drawing the structure. This is my ethene, I told you. So I think most of you would have got the structure. It should be C double bond C and a H2H on both sides. Correct? So how many of you got the structure? I think most of you would have got it, right? Okay. So this kind of thing we saw even in your alkyne. We took it as example for sp hybridization, isn't it? So here you have 2 carbon atoms, right? I told you either one of them you take and do the hybridization. So if you do for this also, it's fine. If you do for this also, it's fine. It doesn't matter. So take any one of them and do the hybridization. Okay. So can you tell me what will be the hybridization here? You know, without even proving it, what will be the hybridization of this molecule? In this carbon and this carbon? Guys? What will be the hybridization?
2.
What do you mean by hybridization is 2?
Three, sir.
Okay, that means what? That means what hybridization?
sp2 hybrid.
Okay, fine. So the thing is, here you see the first bonding atom, second bonding atom, and third bonding atom for this carbon, isn't it? No lone pairs, isn't it? Why? Because there are 4 valence electrons, 1, 2, 3, 4. All of them are involving in bonding. There are no lone pairs here. Understood? Right? Okay. So obviously, I can say the steric number is 3, and it is sp2 hybridized. Okay, now prove it to me. Go for the orbital diagram. And please make sure that you are going to account for 1 pi bond also. Okay, everybody got it? And I'll do. Say for this carbon atom or any of these two carbon atom, it is 1s2, 2s2, 2p2. First, the ground state, 2 electrons in 2p. Now in excited state, this will go here. Done. Oh, now you know what is the hybridization? Hybridization I found out to be sp2, right? So I have three sp2 hybridized orbital, all having single electrons. Okay, all having single electrons. Now what is going to happen? There are going to be three sigma bonds, first sigma bond, second sigma bond, and then sigma bond within carbon also. So I can tell that for this carbon atom is going to give, for this hydrogen atom is going to give, for this also hydrogen atom is going to give. Three sigma bonds are over. And how do you account for the pi bonds? See, after the hybridization is over, sp1, p2, sp3 is over, still you have one unpaired electron. So that unpaired electron here and another electron, unpaired electron here for carbon here. Now they will undergo lateral overlap to form this pi bond. How many of you got exactly this?
I got, sir.
Anybody else? Or how many of you got most of this? Like say 90% correct, sir.
I didn't complete, sir, but I didn't complete doing it.
Okay, so okay, before that I started, or if at all I would have given you more time, you would have completed. Is that what you're telling?
Yes, sir, maybe.
Okay, what problem you faced, Kana?
I took time for me to think, sir, properly.
Okay, that is understood. Obviously, that is perfectly bound to happen because it's the first time you're doing it by yourself. It is perfectly bound to happen. Others, did you even try, guys?
I have a doubt. Can I ask?
Yes, Kana. Yes, Kana.
Sir, for the pi bond, no, sir.
Pi bond.
How
Yeah.
can we express it in our test paper, sir? Like what's happening? How we are taking it as a...
You can just tell that after the hybridization, this is this pure p orbital, right?
So we say it's bound. It will bond with the other pure p orbital.
Exactly. It will again for this carbon atom also you can do the same exact thing. So you'll find that again this also has an unpaired electron like this after the hybridization, right? So two p orbitals having one electron each in these two carbons will laterally overlap to form a pi bond. That's it.
Okay, sir.
Right. Okay. Right. So we saw a good number of examples for sp2. Now we'll go for sp3. I was asking, guys, everybody at least tried, or how many of you chumma sat like that? Abhishek, Mithun, Nagarajan, everybody tried.
Last class I missed it, sir, so I was not able to understand the concept.
Very good, very good. Okay, others. Divya, Bavadarni, everybody tried. Pranav.
Yes,
Okay. What problems you faced, Bavadarni or Divya?
sir, I just now told no, sir. I was not able to.
Oh, you only told. Okay. Sorry. Right. Divya, what problems you faced, Kanna?
Same, sir. I was thinking for the initial stage of.
Okay, cool, done. So you will be able to get it. Okay, do not worry. Right, fine. So we'll go for sp3. Before this, what is the shape and what is the geometry of this molecule?
Trigonal planar is the geometry.
Shape?
Shape, it won't be bent, sir.
Yes, sir.
It won't be bent. Okay. So yeah, this is going to be trigonal planar only, right? Both. I told you, whenever you have there's no lone pair. There's no lone pair in the molecule, right? So I'm going to have the shape and the geometry to be same, right? So here for this molecule, shape is trigonal planar, geometry is also trigonal planar because there is no lone pair here. Okay. So as you said, the answer is correct. It is not bent. Yeah, absolutely true. Okay. Okay. So we we'll take sp3, steric number 3, sp3. Okay, so first itself, okay, fine. So sp3, say for I can again have combinations. I can have ab4, right? That's like how I had in sp2. I had ab3 and ab2l, right? So here also I can have ab4, I can have ab3l, that is 3 bonding atoms and 1 lone pair, or I can have ab2l2. All these combinations are possible.
Sir, S should be equal to 4, no, sir, for sp3.
Oh yeah. Thank you. Yes, s is equal to 4. Right? So s is equal to 4 and sp3 hydroxide. Yes, thank you. So you can have all these 3 combinations coming here: ab4, ab3l, that is 3 bonding atoms, 1 lone pair, or 2 bonding atoms, 2 lone pairs. All of them will give me steric number 4 sp3 hybridization. Okay. So first, like without even going into this lone pair, we can decide the geometries, isn't it? Because geometry, for geometry, whether I have a lone pair, for other, whether I don't have lone pairs, for all these molecules, geometry is a new thing. Okay, it is going to be called as tetrahedral. Okay, have you ever heard this term, tetrahedral? I think you wouldn't, right? Fine. So this is how the shape is going to look, right? So again, it's all based on VSEPR. It's all based on VSEPR. I have to make sure that, say, if I take this AB4, I have to make sure that the repulsions suffered between these 2 bond pair, or these 4 bond pairs, should be minimum, right? So I have to make sure that I put the maximum distance apart. And this is how the geometry is, like this is how the exact shape or geometry is. So you have A, B. Now, whenever I put these 2 bonds, like, okay, basically these 2 B's are in this plane only, in the board of plane only, these 2 B's are there, right? But the other 2 B's, the other 2 bonding atoms are going to come, are not going to be in this plane, right? So a linear shape as well as your trigonal planar shape, all the bonding atoms were in this plane. All the bonding atoms were in this board of the plane, right? This is the first time you are seeing a 3D structure. This is the first time you're going to see a 3D structure. So how will I represent a 3D structure in a 2D plane? This is a 2D plane, but I have to make sure that I have to make you understand that this is 3D. So for that, we can use some representations. Okay. So what we can do is, so this is how it's going to be. Okay, or better words, something like this. Okay, so what does it represent? What does it say? Now you're seeing 2 different types of representation. This is a wedge, right? And this is a dash line, wedge line, dashed line. Okay, so these 2 represents whether the bond is coming towards you, that is the bond is coming like this, or whether the bond is going inside. Obviously, it is not in the same plane. That's what you need to understand. Okay. So now remember, wedge represents the bond is coming towards you. Right? The bond is coming towards you. And whenever I say dashed line, it is going away from you. This is the easiest way to remember. Okay. Whenever I say wedge, wedge is coming towards you, and if it is dashed, it is going away from you, right? So this B is coming towards you, and this B is actually inside the board of the plane. Okay, and this shape is what is called as tetrahedral shape, right? So many carbon compounds, so many organic molecules will have this shape only. Again, given that carbon atom is sp3 hybridized, because we're seeing only for sp3 hybridization. Okay, right? So you can have a tetrahedral shape, right? And what about the bond angles, right? So bond angles, you will not be able to predict that easily. I will tell you what is the bond angle. Remember, the bond angle is 109 degrees 5 minutes. You have to remember this, right? The bond, there's a special thing called as tetrahedral bond angle, right? So tetrahedral bond angle is 109 degrees 5 minutes. Okay, 109 degree, 5 minutes is the bond angle for tetrahedral. Okay, fine. So all this we understood. For all these molecules, geometry is same, right? But okay, what about AB4? What about AB4's shape?
Tetrahedral, sir.
Correct. Blindly say it. Whenever you have same hybridization but no lone pair, shape and geometry are same. So in this case, it doesn't have a lone pair. sp3 hybridized. So geometry and shape both are tetrahedral. But for these two, it cannot be. For these two, only geometry is tetrahedral. Shape is going to be something different. That we'll see what it is later. Okay. Now everybody understood the connection between shape and geometry. Okay, you will get it more and more. Do not worry. Okay. Now we'll take some examples. We'll take example for AB4, AB3L, AB2L2. All of them will take some examples. So guys, shape, you have to remember, this is how you have to draw the shape in your exams also. Tetrahedral, wedge and dash. You have to remember. Okay. So I'll take the beautiful example. First, I'll take AB4 under this. I'll take CH4, methane, very famous example. Isn't it? You are going to do it. Do it. And you know what is the hybridization? You tell me whether are there any pi bonds or whatever it is. Prove it to me that it is sp3. Go for it. Draw the orbital diagram. Who told last class you're absent? Mithun, did you tell that you were absent last class? Mithun, is that you who told?
Yes, sir. Yes, sir. I went off class too, sir. From hybridization, I didn't listen, sir. I went
Okay,
off.
you can look at the video.
Yes, sir.
I think there'll be 2-3 videos you have to watch.
Okay, sir.
Okay. I think this time would have been sufficient. You have to do it for carbon only. You know what is the electronic configuration of carbon. You have to go for the ground
Done,
state,
sir.
excited state, and then go for sp3. Okay, very simple. 1s2, 2s2, 2p2, ground state, excited state, coming for you. Yes, this electron is shifted here. Done. So what is the hybridization here? I know it's sp3, sp1, p2, p3. Done. Right. So you have 4 numbers of sp3 hybridized orbitals, each having one electron, and you have 4 hydrogen atoms. You have 4 hydrogen atoms giving one electron, completing the sigma bond, 4 sigma bonds. Okay. So you know how the shape is going to look. Shape is exactly how we saw for AB4. Just I'm drawing it again. C H and a H. Right? This is how the shape is going to look. Right? Cool.
Yes, sir.
Right? So I think this time I think more number of people would have gotten it. I suppose. I hope.
Yes, sir.
Right? Okay.
Yes, sir.
Good. Very good. Right. Fine. We'll take more examples now. Again, the shape and the geometry. Shape and the geometry both for this molecule is tetrahedral. Right? Shape and the geometry, both the things for this molecule is tetrahedral because there is no lone pair. Okay. We'll move on to other example. Oh, I'm sorry, guys. Was someone copying? Did I rub it off? I'm sorry. If at all, you can just watch the video again. I'm really sorry. If we're copying. Okay. Now, let me take an example with pi bond. Let me see if we can do this. Okay. SO4 2 minus. Right. SO4 2 minus. Guys, don't panic. Just by looking at an ion, please do not panic. It's the same thing. Now, I'll give you for a trick for this also. Right. So whenever you have negative charge, it has to go to the bonding atoms. Negative charge to the bonding atom or the side atom. Or sometimes what will you do is you will give it to the more electronegative atom. Right, whichever out of the central atom and bonding atom, whichever is more electronegative, to that thing you will give the negative charge, right? So obviously you can see sulfur, oxygen. Obviously oxygen is more electronegative, right? So the two negative charges has to go for two of the oxygen two of the oxygen atoms are having -1, -1, totally -2. You can either go by more electronegative atom, or you can see that the side atom here is oxygen, right? So obviously that is the bonding atom and that will have the negative charge. If it is positive charge, generally it will go to the central atom or the less electronegative atom, right? That's less electronegative atom. Okay, fine, you do this. You know the structure for SO4 2 minus, right? So you would have had, this is what you would have had. We even did the Lewis structure for this, isn't it? So this is mine. Done. So how will I find the hybridization first? First go for the bonding atoms. 1, 2, 3, 4. 4 bonding atoms. No problem. Now I have to check whether I have any lone pairs on sulfur, right? So there are 4 bonding atoms, and I have to check whether there is any lone pair on sulfur. Sulfur belongs to oxygen family, right? So it also has 6 valence electrons. Sulfur has 6, 2, 8, 6 would have been the configuration for sulfur, isn't it? Now see how many electrons involving in bonding here. 1,
6.
2, 3, 4, 5, 6. That's it. All the 6 electrons are involving in bonding here. So there are no lone pairs. So steric number is 4. So definitely it is going to be sp3 hybridization. But what you have to do is prove it to me. Go for it. So please understand that you have to account for 2 pi bonds, 1 pi bond, second pi bond. Sulfur will have 3s2, 3p4 valence electron configuration. And you have 3d also there. Okay, this is going to be a little tricky, I guess. So for sulfur, you have 1s2, 2s2, 2p6, 3s2, 3p4. Now, if I have principal quantum number of 3, right, I can have 3s, 3p, and I know I have 3d also, but it is empty. Right. Now, why am I saying this? Is because when you're going to the excited state, you are going to put the paired electron in the next empty orbital. You can even go to D, no problem. But why in other things till now what we saw, we didn't do this because we saw examples only till 2. That is principal quantum number of 2. That's why I didn't have any D orbital. But if I have 3, I have D orbital also to be present, but it is empty. You can put the electrons there. No issues. Right?
Done, sir.
Okay, good. So first, if I draw the ground state, in ground state, I'll just start with 3p, 3s, and 3d alone because that is my valence shell. So 3s, 2 electrons. In 3p, 4 electrons. And in 3d, no electrons. No problem. Okay. Now I have 2 paired electrons, this and this. I have 2 paired electrons, isn't it? So I will not be able to shift this to here anywhere because there is no lone pair. If at least there is lone pair, I can shift inside the hybridization itself. So that is not possible now. So I have to make sure that the paired electron, one of them is going to go to the empty orbital. That is my D orbital here because that is only empty. All the other orbitals are filled. I don't have space. I'm writing at the top. Right. Say now in the excited state. So you will have, sorry. Okay, so one electron. So I have this electron and this electron has gone to D orbital. 1, 2. Done. This is my 3D. 3p. 3s. Okay. Now we already understood what is the hybridization. Hybridization is sp3. So we'll take sp3. Done. Okay. Now you can see after the hybridization, there is still 2 more unpaired electrons, indicating that there is going to be 2 pi bonds. Yes, I have 2 pi bonds here. So, okay, if I can make this, so I have 4 numbers of sp3 hybridized orbital. Oops. Okay, fine. Each having one electron, right? So there are going to be 4 oxygen atoms, each giving 1 electron. Done. 4 sigma bonds. 1, 2, 3, 4. 4 sigma bonds are done, right? And obviously, I am going to have 2 more unpaired electron on sulfur, and oxygen atoms are going to have unpaired electron laterally overlapping, forming first pi bond, second. Okay, fine. So now that's it. Today's class is over. I don't think we have time, but I'm going to give you a homework. Okay. So what you're going to do is, you are going to find XCO3 molecule. You are going to do the same thing as what I did. Find the hybridization. Prove to me that that is the hybridization and account for the number of pi bonds. Okay, and lone pairs if any. Right. And next, you are going to go to XC. Okay. And one more thing is you are going to do for NH4 plus ammonium ion, right? For this also you are going to do what is the hybridization, what is the number of lone pairs, if there are any pi bonds, all these things you are going to prove it to me. Okay, so for these 2 molecules, this is your homework. It will take only 2 minutes. Just you have to think and do it. Okay, fine. So we'll continue with lot more examples, right? More complex examples. All these things we'll saw next class. Okay, guys. Until then, we'll see. Bye bye. Thank you.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.